Projective geometry. What is it, and what do floor tiles, mathematicians, and Italian artists have to do with each other? To answer these questions, we gotta go back a little bit to ancient Greece. Much of the foundational geometry that we do is a direct result of a guy named Euclid. This Grecian mathematician wrote a textbook called The Elements, in which he describes a set of postulates that serve as its premise. Some of these postulates include things like, you can draw a line, or you can draw a circle. Pretty simple. His fifth and final postulate is famously known as the parallel postulate, and can be defined as follows. If a straight line intersects two other straight lines, and the inferior angles are less than two right angles, then the two lines will meet eventually. We can deduce that if the angles are right angles, they will never meet. We define these lines as parallel. Basically, Euclid made some rules to define his math world, but what if we change those rules a little bit? That brings us to projective geometry, which asks the question, what if parallel lines do meet? It became clear to artists around the 15th century that they can profit off of this idea. Utilizing the idea of vanishing points, essentially parallel points meeting at the horizon, artists like Filippo Brunelleschi started making paintings appear more realistic, making pieces look like this instead of this. Eventually, this paved the way for pieces to start looking like this. It wasn't just in the art world that projective geometry started to become considered, however. Mathematicians also began to consider the idea. Before we dive into what happened, we first need to understand the concept of coincidence, and we can do this by drawing some tiles. I know, right? Who knew that mathematics and interior design could sometimes intersect? But okay, if we start by drawing a horizon line, and then two lines to make the corner of the floor, we get something like this. Next, we can arbitrarily draw the first tile going to the horizon. If we draw a new line that goes through the intersection of these two, we can make a new point that goes to the horizon. Now, we can draw another new line that starts at the corner of the tile and goes to the horizon. This new intersection can be used to make another tile. We can continue this until our floor is complete. We can see now that we've discovered something. Automatically, there is a line that intersects 3 points. 2 points will always be incident with a line, but if a third point is also incident, well, that's a coincidence. Okay, that's great and all, but how does coincidence relate to projective geometry? Well, coincidence is precisely what the theorems of projective geometry set out to explain. There are 3 major theorems of projective geometry: the Pappus theorem, the Desargues theorem, and the Little Desargues theorem. The Pappus theorem says that if you have 2 straight lines and points A, B, C, D, E, and F, and they are linked like this, then you can draw a line through the intersections. 1, 2, 3. That looks like a coincidence to me. This was found in 300 CE and was the first solely projective statement ever discovered. Now let's move on to Desargues' theorem. This one was discovered by, you guessed it, Desargues, who is widely credited as one of the founders of projective geometry. This guy said that if you have 2 triangles where the lines through their vertices pass through a perspective point called P, then the intersection of each corresponding side lies on a new line. 1, 2, 3. Again, this one shows that just like lines, 2 planes in projective space can also meet coincidentally at a line. Now, let's move on to the Little Desargues theorem. This one is really just an extension of the Desargues theorem, but it has some implications that I will dive into later. This theorem simply states that we can draw 2 triangles that again are in perspective from a point P, and again have corresponding sides that make a line. But now, this new line also goes to P. This is important because it can be used to show why the coincidence with the tiles was happening. Again with the tiles? Yeah, again with the tiles. First, before we begin, let's remember that we are in projective space, so if lines meet at the horizon, then they can look parallel from a different perspective. So, we can redraw the Little Desargues theorem to look like this, where we can't even see perspective point P anymore because the vertices lines now actually look like normal parallel lines. From this vantage point, we realize that in this situation, if you have two sides that are parallel, then the third must also be parallel, because before we saw that all of the sides met at the same line that went through the perspective point P. Alright, now that we've got it cleared up, let's look at our tiled floors again, but this time viewing the lines as traditionally parallel. We've got our dashed and solid lines again, and we want to show that the dashed line is parallel to the solid lines using our new theorem. Essentially, we're using the little Desargues theorem to show why there was a coincidence with the tiles. We can now draw our triangles again from the little Desargues theorem. This is really the same as before, as the lines from the vertices are all parallel. Alright, so we know that the red and black lines are parallel because we drew them like that. But what about the blue lines? Well, these lines are also parallel because of the little Desargues theorem. Remember that if two sides are parallel, then the third must be also. Great, now we're almost there. We can draw a new set of little Desargues triangles, this time looking like this. We now know that the blue lines are parallel, and that the black ones are because of the way we drew the picture. This means that our last two are parallel. We just showed that our dashed line is parallel to the other two, and why it meets them at the horizon. Something we knew visually can be proved mathematically. Alright, well, who cares about all this? I think we all should, because as we've seen, sometimes there are benefits to viewing mathematics through a different light. Sometimes redefining the rules, even ones as fundamental as two parallel lines will never meet, can have an impact on the way that we view the world. It's amazing how sometimes throwing out the playbook and making new guidelines can solve problems, even ones that we didn't even know we had. However, for your next geometry exam, maybe be careful in boldly proclaiming that parallel lines meet up. It likely won't go over very well.